uncertainties. And furthermore, so this enables us to quantify the uncertainties for individual factors, which is much easier to quantify the uncertainty for the final scenario. And in addition to this, if we remain flexible enough as engineers, then probabilities can be interpreted as both frequency or the degree of belief, so that it provides us with a means to perform the multidisciplinary analysis by combining physical and social science, which often come in quantitative and qualitative evaluations respectively. In other words, in summary, we need to perform the probabilistic analysis over such complicated settings. Then how can we do this? To this end, Bayesian network is a useful tool because it graphically represents a probability distribution and thereby facilitates modeling the causal relationship between random variables, while such a causal relationship is quite apparent between real-world variables. So here, by random variables, we denote those variables whose values cannot be determined with certainty, but rather would be one of those possible values with some probabilities. So in a Bayesian network, each random variable is represented by a node, and the directional edges between those nodes represent the directional dependence between those variables. And the causal relationship is an example of directional dependence. And given a Bayesian network graph, it is very straightforward to formulate the distribution, because what we have to do is simply assign the distribution to each node being conditioned on their parent nodes. Then the joint distribution becomes simply the product of the conditional of the distributions that are assigned to all of those nodes. So for example, let us consider this EMA highway benchmark in the USA and assume that this network is subjected to seismic hazards. And we are interested in the connectivity from the source to the terminal nodes for evacuation purpose. Then we have these 129 roads with uncertain performance, which can be represented by these 129 component events, which apparently determine the state of the system event. And we also have this hazard event, earthquake event with uncertain magnitude and location, which affect the performance of those roadways. And we have this deterioration status that affects the seismic performance of those roadways as well. And this deterioration status can be inspected with some error through these inspection nodes. So this is how Bayesian network facilitates modeling complicated real-world systems. And not only does Bayesian network facilitate modeling, but it also facilitates probabilistic inference, because there is a suite of well-established algorithms for which even automated inference is available by using general-purpose software programs like Genie. And the reason why those algorithms are easy to implement is that they are just based on three basic operations: conditioning, product, and summation. So by conditioning, we can narrow down the distribution by leaving only those instances that are compatible with a given evidence. And by product, we can merge the random variables by multiplying the compatible instances. And by summation, we can marginalize out a random variable by summing up all those variables, all those instances that are compatible with each other with regard to all random variables, but the ones that are being marginalized. So for example, in the Bayesian network that we saw a moment ago, if we want to update the system reliability using the inspection results, what we have to do is first condition the inspection nodes and repeat the product and summation until we end up with only the system events so that we can update its probability. So in the same regard, we can compute the marginal system reliability by not conditioning the inspection nodes at the first step. And we can even compute the component importance measure by leaving the component event of interest as well. Then let us look at how this methodology can be applied for real-world problems. So as part of tomorrow's cities, as part of the research project Tomorrow Cities, Professor Dina Dialla and I are currently investigating the multi-hazard resilience of an urban transportation network, where our case study area lies in Istanbul, Turkey. And in order to analyze this system, we set up our Bayesian network where we have these hazard nodes which affect the physical damage state of the paved roads, bridges, and buildings. And we are also considering the debris pouring from adjacent buildings and overpasses, and the level of physical damage and the amount of debris together determine the speed of recovery. And all of these three factors together determine the performance of those roadways, from which we can compute the history of the network's performance. And finally, by assembling the performance at each time window, we can compute the resilience of the whole system. And as we've seen in the previous slide, the resilience analysis of urban real engineering systems involves a lot of data and tools, and Bayesian network can synthesize all of them using its graphical representation. So for data, we collected GIS data of hazard maps, roads data, and building distributions. And we also gathered structure data as fragility curves as structure information, which were classified using bridge drawings and satellite imagery. And we also had to gather the relational data so that we can connect the nodes in the Bayesian network, such as structural damage and the traffic capacity of the roadways, and the structural damage and the repair process. And we are also using different types of tools, such as structural analysis, network analysis, probabilistic inference, and GIS software, all of which could be combined using the Bayesian network, and thereby we could produce the vulnerability map. And resilience analysis ultimately aims to support the real-world decision-making tasks. And in our project, we are particularly focusing on the disaster inequality issue through our system. And from the discussions with local stakeholders and researchers, what we've identified as the primary source of inequality is the prevalence of the unlicensed buildings across the city, whose insufficient structural capacity might encourage them to collapse onto the roadways and create secondary disruption of traffic, and thereby create some unequal mobility in an emergency situation. So in order to investigate this issue, we investigated the spatial distribution of the vulnerability, as well as the correlation between the vulnerability and the building distributions. And what we found was that high building density is likely to increase the vulnerability, but nevertheless, network topology is the most significant factor in terms of systems vulnerability. And So as we've seen so far, Bayesian network is a useful tool and has been well explored until now. However, Bayesian network has still has a great potential for development, regarding which I'd like to introduce some of the recent efforts as well as remaining tasks. So the first challenge worth noting is Bayesian network experiences difficulty when it tries to handle large-scale systems. And this such difficulty arises from the converging structure between the component event and the system event, by which we need to quantify the distribution of the system event. And as we can see here, there's the number of the joint states of those random variables exponentially increases with the number of components. In other words, we need an exponential order of computational cost and memory demand to compute and store these probabilities. And in order to address this issue, efforts have been made rather in two branches. So first, we can think of efficiently encode the regularity in the system events definition, so that we can address the memory issue. On the other hand, we can perform the approximate inference in the framework of Bayesian network, so that we can use only a subset of instances for our inference. And this approach can be classified into two again, for computing the deterministic bounds or computing the stochastic approximation, in other words, sampling. And recently, as part of my PhD work, I graduated from Southern University about a year ago. And as part of my PhD work, we proposed matrix-based Bayesian network as an effort to unify all of those previous efforts in a single platform. And to this end, we proposed an alternative data structure of the distributions using matrices. And if you are interested in, you can refer to this reference. And the second challenge that I'd like to talk about today is optimization, so that we can provide more direct decision support. And in this regard, extending Bayesian network for optimization is quite straightforward, which is then it is called inference diagram, ID. And the only difference between BN and ID is the two additional types of variables, namely decision variables and utility variables. And in inference diagram, the objective function becomes the sum of the expected values of those utility variables. So, for example, in this truss bridge system, if we want to optimize the cross-section areas of those 25 members, then we can add 25 decision variables to take this into account, and we can evaluate the design cost and the system performance. However, despite such straightforward extension in a graphical way, computing ID is not very straightforward, for which I'd like to point out two common challenges that we face. First, civil engineering systems often involve multiple objectives, in which case we might want to get a set of non-dominant solutions instead of picking a single one. For example, in this Bayesian network, we are considering both the cost and the system performance. On the other hand, the second challenge is that, especially when we try to evaluate the system's performance, we again face the exponentially increasing complexity of optimization with regard to the number of components. And in order to address this issue, a few efforts have been made. And of course, the most popular choice is using meta-heuristic algorithms such as genetic algorithm. But recently, as a part of my PhD work, we proposed an approximate optimization by proposing a proxy objective function which effectively emulates the exact objective function, with which we could get a set of non-dominant solutions for this truss bridge system. And if you are interested in, you can refer to this reference. And still, there are many interesting topics worth investigating further, regarding which I'd like to suggest 3 topics. First, we can think of the sensitivity analysis and uncertainty quantification within the framework of Bayesian network. And this is particularly relevant because Bayesian network involves multiple tools and data, all of which come with a great level of uncertainties. And therefore, we need to be able to systematically analyze their impact on the analysis results so that we can effectively control them while designing the efficient plan for data collection. The second topic worth investigating is the automatic quantification of arbitrary system events. So as pointed out previously, Bayesian network faces difficulty when it tries to handle large-scale systems, and the previous efforts that try to encode the regularity in the system events definitions or develop some customized algorithm for a given system event type, such as network connectivity and flow structure systems or system and series and parallel systems. However, if we can have some general algorithm that can handle any arbitrary system type, it will be greatly helpful. And finally, we can generalize the probabilistic graphical model because Bayesian network is a representative of only those problems which can be represented by directed acyclic graphs. In other words, the random variables have directional dependence, and there is no cycle in the graph, and thereby there's no feedback effect between the variables. However, there are a broader set of dependence in real world, such as undirected dependence, as in Markov random field, or bidirectional dependence, or feedback effect. And by bringing those a broader set of dependence to describe real-world problems, we'll be able to enhance our capability. So in summary, analyzing the resilience of civil engineering systems is a challenging task because we have to deal with large-scale systems that are affected by various dependent factors, and thereby we need to perform the probabilistic analysis over such complicated settings. And to this end, Bayesian network is a very useful tool because it enables us to handle complicated real-world systems by facilitating modeling the joint distributions using the causal relationship between real-world variables, and also by making inference systematic and automated. And thereby, we can synthesize multiple types of data and tools for our probabilistic analysis. And still, Bayesian network has a great potential for development, regarding which I introduced some recent efforts to address the issues of large-scale systems and the Bayesian network optimization. And still, there are some other topics worth investigating, such as model validation, automatic quantification of arbitrary system types, and generalizing the graphical representation of real-world problems. And thank you for listening.
Thank you very much. As always, very interesting. Well done. Very interesting that you are introducing the feedback in your Bayesian network, as well as the traffic distribution and disruption by the debris was very interesting for me. As always, the floor is open for any questions, and please raise your hand and please feel free to unmute yourself. Okay, I can see Ahsana raising her hand, please.
Hi, can you all hear me, Will? Yeah?
Yes.
Okay, this was very interesting. Thank you for the presentation, first of all. I have a few questions. I mean, I don't know where to start with. I will go with this. You are considering a system or a network that is fixed in time at one point of analysis, isn't it? Like, my question is, are you considering a dynamic system which is changing with time? Or is it like one snippet of time that you are looking at, and how the probabilities evolve within that time?
Yeah, actually, we are considering the dynamic process of the system states because we are considering this recovery process. So in the resilience analysis, we are also interested in how rapidly the system recovers its original functionality. So usually when we reliability analysis, we usually say about more static analysis. But if we go to resilience analysis, we add this time dimension to understand the recovery process.
Could you please explain how do you do that? Do you introduce
so it
that?
is just like yeah. So in this Bayesian network, actually the box indicates the repetition of this structure. So we add a bunch of these two nodes for each time node, each time scale. So there's this t variable. Yeah, and when we compute this vulnerability, we all bring those nodes together to evaluate this node. So it's a very huge problem, and actually it is quite expensive to run this network. For instance, for this network, it took like 5 days. So it's quite a huge one. And yeah, and it is also, so that is why we had to resort to sampling. So it was not deterministic evaluation, but it is rather sampling with some, of course, with some uncertainties arising from the sampling.
Okay, thank you so much.
Thank you.
Before moving to Karim, can I ask you a question very related to what Ahsana was asking? When you say you are considering the time in the network, is this the traffic distribution? Are you considering how much heavy the traffic is? Is it daytime, nighttime? You're considering all of those?
No, actually, this is quite a in the network analysis part, it is just the maximum flow analysis. But so what we are measuring here is when an earthquake happens, how the function is deteriorated compared to its original capacity. So we are considering kind of about around 10 to 20 destination nodes that connect to the arterial roadways. And we are considering the maximum flow to those arterial entrances from its local location. So
okay, so it's like a worst case scenario. Yeah. Okay. Karim, if you want to, yes, sorry. Karim, if you want to unmute yourself and ask
thanks a lot. Thanks, Ji-Eun, for your presentation. I have two different questions. One of them is regarding the size of the data and whether you are using high performance computing for handling your data. Because I was thinking, by doing some importance sampling, like trying to find the optimal point of damage, you would be able to reduce the size of your simulation. So that was my first question. I'll ask the second one because my network is unstable, and just listen. This example you showed for the network performance, including the structural damage, there was a figure on the right side of the presentation in one of your slides. Mm-hmm. You mentioned that the network, I think this was something similar to this maybe. The network performance is, this is what I got, more important on its own in comparison to the performance of the nearby structures. Is that correct? Or the effect of nearby structures is less compared to the performance of the network itself?
So you mean by network itself, the roadways?
Yeah,
right?
I think, yeah.
Yeah, I think according to the analysis result, of course, the structural performance of those roadways is much more important, but compared to the performance of the adjacent object, but when it comes, it seems that apart from all of those factors, network topology is the most significant factor, because the vulnerability is determined by, governed by how well connected all those locations together. And so.
This would depend on the problem definition. So you could imagine roadways and bridges that are nearby slopes and buildings. And the performance of those, I would imagine performance of the slope in terms of slide and also the structures will be more important, because any damage to them will block the road. So that's what I was thinking. I think this would depend on the problem's setup. Thanks a lot. I wouldn't talk more than this, but I would like to hear your thoughts on the utilizing HPC and parallelizing the work, in addition to importance sampling, because with my, I mean, this could be, I don't know how you would do importance sampling for a complex networks. So I would like to hear your thoughts on this. Thanks a lot.
Yeah, I just use personal computer to compute this Bayesian network, but since I'm using only Monte Carlo simulation, this is perfect situation for utilizing high performance computing or parallel computing if the resource is available. And for importance sampling, it is a bit complicated because there's two issues. First is that it is not straightforward to perform importance sampling effectively in Bayesian network. And the second is that the performance of those roadways is discrete variables, and for discrete variables, importance sampling is not really straightforward, because it is not easy to formulate the importance sampling density effectively. But still, I think it is a very important question, and that is also one of my future research topics, about if finding the optimal density sampling density for discrete Bayesian network.
Thanks a lot.
Okay, perfect. Hossein, if you want to ask your question, please unmute yourself.
Sure. Thank you. So this is Hossein from ETH Zurich. Thank you so much for your presentation. I just had a quick question regarding the granularity of your model, and specifically about this figure. I was wondering how granular you need to model your network. Do you need to model component by component or region by region? So how detailed you need to be to model your network? Thank you.
Yeah, so actually we are considering all those buildings and roads individually. So there are around around 5,000 roadways and like thousands of buildings, as you can see in this map. So it is, yeah, so we are considering all edges individually, and that is part of the reason why the analysis is taking so long. But I think there is always the trade-off, and we can somehow balance the resolution. Yeah, but in this analysis, we are considering individual roadways and buildings.
Okay, thank you. So do you have only one Bayesian network, or do you have lots of Bayesian networks, one for each component?
No, each component just comes in here to compute their damage, and they are all within the same Bayesian network.
Okay, thank you. Thank you so much.
Okay, perfect. Before getting to Tom, I have a very similar question to Hossein. My question is regarding the debris. How are you going to model them? Like, are you considering the typology, the height of the structure? Like, there will be so many like options. Are you going like a binary approach, failure, yes, no, and then if it's failure, network will fail and we carry on? Or are you doing like a proper probabilistic analysis of the most common types?
Yeah, actually that is the most tricky part, because it is very, there is no much data that we can exactly model how the debris or adjacent collapsing building would disrupt the road. But so it is just a set of bunch of assumptions, and that's why I emphasize the need for uncertainty quantification or sensitivity analysis of those parameters. But in this model, what we are assuming is that first we are given the height, the number of stories for each building. So for each building, we assume that any roadways that is within the 60 meters from the centroid of the building is within the inference of the buildings. And then we say if the building is in the demi-state of extensive, then the one lane will be blocked. And if it is in the complete demi-state, then all lanes will be blocked. And after that, we assume linear reduction in the debris length, so that we can model the recovery of the traffic capacity.
Very interesting. Tom, if you want to unmute yourself and ask your question.
Hi, yeah, first off, thanks for a very, very interesting presentation. I'm very interested in the indirect impacts. So in your multi-hazard resilience of the urban transport network, I'm assuming an objective is to maintain flow through the network to get people away from the disaster area and emergency services in. But how when you're looking at the resilience, do you factor in things that are dependent on different systems? So the power system may have been disrupted by the same event, and the traffic light network could then be out as a result of that. So you could have beautiful road surfaces undisrupted by the event, but if your traffic light system is disrupted, how do you maintain the flow? So think indirect impacts like that. How do you factor them into a model like this one? Or am I missing a point?
So you mean how we can incorporate our emergency response in the model? So
I mean, the contingent probabilities will change when there's a hazard event. And I was just thinking interdependent things that could fail and change the dynamics of your system related to another infrastructure system being affected by the same hazard simultaneously. Whether that's beyond the scope, whether that's something you've done and I've missed that.
No, we are only considering the collapses of the damage of buildings and roadways, and not other than that. But of course, the interdependent infrastructures have been a very active research area, and I haven't addressed that issue yet, but my impression is that the most challenging to do so will be modeling the interdependency between those variables, those two different systems, because we really do not have a much model or data or understandings of how they exactly interact with each other. So usually when we try to consider multiple systems or multiple hazards altogether, I think the most challenging is that we do not really have enough data to model their interactions. But yeah, but I haven't addressed that issue yet, but it is really an interesting topic worth investigating.
Thank you for your answer. Yeah, it was just as infrastructure becomes increasingly smart, I was wondering how you factored that into your
that is true.
models.
Yeah.
But no, really appreciate your presentation and your answer. So thank you so much.
Thank you.
Perfect. Very interesting question. For sure, like the post-disaster is very important as well. A failure of a simple traffic light. And imagine how much collisions and how much heavy traffic you will cause, and then this will affect your emergency response. So this is where resilience comes into play, and we have to consider that massively. Our MSc students this week are gathering all of the stuff that they have learned through term 1 and term 2, and they're seeing it, how it's applied in resilience. So thank you very much for this presentation. It's the last point of our studies in MSc of Earthquake Engineering. Anyone has any other question? No? Okay, perfect. So again, thank you very much for your very interesting presentation, very useful. Good luck, really good luck with all of those computations. Probably you will end up using AWS servers and stuff like that, but yeah, I'm sure you'll be successful. If you don't mind, I'll just share my screen and I will just talk about the last presentation of March, which will be by our colleague Andrea Francini. He will be talking on probabilistic optimization of seismically excited cable stayed bridges. This will happen next Wednesday, 24th of March, at the same time in the same place. And then we'll have the short break and hopefully we'll come back in June, July. So thank you very much. And if there's nothing else, we'll see you next week. Thank you very much for everyone joining. See you later.
Thank you. Bye.
Thank you.